peeps looking for something to do with those peeps you have? Well, might I suggest a microwave tool? It's a great way to demonstrate the ideal gas law.
The ideal gas law tells us about how gases behave under different circumstances. And the really cool thing about gases is that we can kind of treat them all the same in terms of because in a gas, the molecules are so far apart from one another, as we'll get into, we don't really have to consider what the molecules actually are. So it doesn't matter if it's oxygen or nitrogen or hydrogen or helium. We can treat them all the same, at least ideally. And it's easiest to think about things ideally. And so that's what we're going to do. And this ideal gas law tells us that the number of gas molecules, so any gas molecules, this is going to be our N, it is so the N times the temperature and this gas constant, which helps us convert things, it's going to be equal to the pressure times the volume. So we have this constant relationship between pressure, volume, number of gas molecules, and the temperature. Because the temperature and the pressure and the volume, they're on different in the number of gas molecules, you have to use two sides of the equation. If we rearrange this different ways, we can see that if we leave one thing constant, something else is going to have to like get bigger when something gets smaller, and something's going to have to get bigger when something else gets bigger if they're on opposite sides. So if they're on the same side, then one gets bigger while the other gets smaller. And then if they're on opposite sides, they both get bigger or smaller at the same time in order to keep this a constant. And so if we rearrange this equation in different ways, we can see the relationship between these different factors, and we can give these different names like different laws. So for example, Avogadro's law is when we rearrange it and say like, okay, well, if we add more gas molecules, they're going to increase the volume, so they're going to take up more space. Charles's law says, okay, well, if you increase the what if you increase the temperature? So if you get, then you're going to increase the volume. Boyle's law, it says if we increase the pressure, we're going to decrease the volume. So we're like squishing these gas molecules closer together so they take up less space. And then Gay-Lussac's law, aka Edmonton's law, it says that there's this at a constant volume, the pressure and the temperature are directly related. So a higher temperature means that the molecules have more energy. This is what temperature is telling us about. It's about a measure of how much energy the molecules have. And when the molecules have a lot of energy, they're going to be banging into things and creating pressure. And so these different ways that we can arrange this equation, and this overall equation is called the ideal gas law. And we can demonstrate this ideal gas law using Peeps and sticking them in the microwave to do a sort of like Peep stool. So what happens is that inside of your Peep, these Peeps are like made up of marshmallows. And so marshmallows are sugar, water, corn syrup, and gelatin. And this gelatin is this mix of polypeptides, so little like protein strands that come from chopping up the protein collagen. So that's the same protein that gives your skin strength. And marshmallows get their like original size by whipping it with air. And so you're getting, when you're doing this, you're getting air trapped inside of here. And so this is why they're all squishy. And so they have this trapped air inside of here. And when we have air, we have gas. And as we said, we have that relationship between the gas molecules, the temperature, and the pressure. So if we put them in a microwave, what we're doing is we're adding temperature. If we add the temperature, well, then the volume is going to have to increase as well. This is what Charles's law tells us. And if the volume, when this is happening, more of the water molecules are going to evaporate and join in. So molecules really, really want to be a gas, but it's hard to be a gas because the molecules are kind of like, they all want to interact with one another. Well, they don't really want to interact. It's kind of like more like they're getting stuck to one another when they're trying to escape and be a gas, because molecules really, really want to be free and they want to have a lot of freedom of movement. This concept called entropy, that molecules like to have as many different like ways to move as possible. Sometimes this is referred to like as randomness or disorder, because they're moving around in all these different ways. If you were to go look, they could be like in any sort of way, and it might seem, and so it's like random or disordered. So these molecules, they want to be free, but they're having this problem because they keep getting trapped to one another. And so if they have more energy, they can break free from those reactions. They can kind of like wiggle around and break free. In a solid, they don't have enough energy. In a liquid, they have enough energy to kind of slide past one another, but not to break all the way free. And then in a gas, they have the energy to become all the way free. And so the ability to become a gas is going to depend on how much energy they have, as well as how much energy is required. So like how sticky are they to one another, and what's the pressure like? So are they hitting each other more frequently, running into things more frequently, and that sort of thing? It's going to be harder to become a gas at a higher pressure or at a lower temperature. So as you increase the temperature, the water molecules are going to evaporate and join in. And so remember this N, this is the number of gas molecules. And if you increase the N, you increase the number of gas molecules. Now you're going to be increasing the volume because these are on opposite sides. So if you increase this, you're going to have to increase this in order to keep this constant. And this is what Avogadro's number tells us. So you're having more gas molecules enter, and those gas molecules are getting more energy. All of this is going to be what all of this is happening. Now you're going to have increased pressure as well, and this is going to be pushing against the walls. And this is going to be making your peeps expand. And when the peeps expand, now they are going to look like they were dueling. What's going to happen? Because they're like trapped in that gelatiny gooey mesh. The gas can't get all the way out, and so it's going to be trapped in here. And this is why you're going to get this peeps expanding instead of the gas just kind of like moving out of the peeps. But what's going to happen too is that when some of the water is going to evaporate when these cool, and when this happens, then the peep is going to get all hard and kind of gross. But in the meantime, you can play with it, and it's really fun. So hope that helps you understand the ideal gas law, and have fun, peeps. And I also have a more serious post on the ideal gas law if anybody wants more details.